Electroosmosis is somewhat like electrophoresis, except for in this case, we're going to use an electric field to move a fluid rather than moving particles. So you've got a container filled with some sort of electrolyte, and we've got a voltage source. We've got a positive electrode and a negative electrode. And we know that that means we're going to have an E field that goes from left to right. Now imagine we put a capillary in there. And I'm not going to draw the capillary to scale. I'll draw it really big so we can look inside it. So here's our capillary. So we're putting it lengthwise in this E field. And let's imagine that our capillary is made out of a material that has a positive surface potential. And of course that means for our purposes it's also got a positive zeta potential. Well, we know that it's going to attract an excess of negative ions because there are counter ions to these coions. So since they're in the solution, we'll put them in blue. So we've got this excess of counter ions and a deficiency of coions, right? There's not going to be as many. We know that there's a 50-50 balance of, say, sodium and chloride ions in solution up here in the bulk, but inside this capillary where we have a positive surface potential, we're going to have more, say, chlorides and fewer sodiums. Great. So we've got this excess of negative charge. Well, those negative charges are going to move counter to this applied field. So we expect the flow of charge of these counter ions is going to be from right to left. Now those charges, of course, are going to be surrounded by hydration spheres, and those are going to get dragged to the left as well. And so the net effect is fluid is going to be pumped in this direction. So we're actually pumping a fluid, in this case water, that is neutral by dragging it using these counter ions. Here's a function of the dielectric constant of the solvent, the zeta potential of the capillary that you're inside of, the applied field strength, and of course it's inversely proportional to the viscosity of the solution. So in this example, we've got a glass capillary. It's filled with a known electrolyte. We put it between two electrodes that maybe we've hooked up to a 9-volt battery, and then we watch how quickly the solution moves through the capillary. And the question is, what is the surface potential of that capillary? Actually, what's the zeta potential? Okay. And all these electrokinetic effects, even though they're caused by surface potential, really what we're looking at is zeta potential. Okay, so a few preliminaries we need before we start. We need to find out what that field strength is. So we've got 9 volts. So we know we can get that by taking the voltage divided by the distance. So we've got 9 volts. We've got a distance of 45 centimeters, 4.5 centimeters. So we've got a field strength of 200 volts per meter. Once again, we need to either look up the viscosity of the salt solution or approximate it with water. In this case, it's pre-dilute, so it actually is going to be very close to the viscosity of water. So 8.10⁻⁴ Pascal seconds. We should put the speed into SI units. So we're moving in the same direction as the field at 0.66 millimeters per minute. So let's get rid of minutes first. Put seconds, 60 seconds per 1 minute. Let's get rid of millimeters. So we've got 1,000 millimeters 1 meter. And then we can cancel those. (1.1, 10 negative 5 meters per second. Okay, so we've got all the pieces that we need. Okay, so we figured out the speed, put it in good units, we got the field strength, and we've got the viscosity. All right, so let's write our equation. So we were supposed to solve this equation for the zeta potential, so let's do that. Permittivity of free space, and then the dielectric constant of water, and then our field strength. And you should, as an exercise, verify this comes out to volts. And what we come up with is a negative 7.0 10 to the negative 2 volts. Or we could say this was a negative 70 millivolts. And then we do a conceptual check on why this should be a negative sign. If we have a capillary with a negative surface potential, we know it is going to attract counterions with a positive charge, and so those positive charges are going to go in the same direction as the electric field, which is what we saw in the problem statement, that the flow of the solvent, which is being dragged along by those ions, was in the same direction as electric field. You can sort of see the origin of this negative sign in the equation is that the charges that are actually in the capillary, that are in the solvent, are going to be opposite in sign. They're counterions to whatever the surface potential of the material is. So our surface potential of our glass capillary was negative 70 millivolts.